Are you sit ups? They've got you set up.
I think everybody was here.
Yeah. Right. Well, people just research good. Well, I guess I should begin. Well, it is my great pleasure, and on behalf of CITA, to welcome Giant Narlikar, who is a giant in India in astrophysics. And he was responsible for the creation of the Inter-University Center for Astronomy and Astrophysics in Pune, bringing together many citizens, Varun and Zaru, and Amir was a graduate student there, and so we have quite close associations with that institute. But I also want to cast back to earlier periods in Giant's history, because this may not be as well known to the younger grouping. He had a very long and fruitful collaboration with probably, well, certainly one of the greatest astrophysicists of the last century, Sir Fred Hoyle, who was created the Institute of Theoretical Astronomy, which Peter Martin was closely attached to, I think even before it lost its teeth.
Fred and I left at the same time and went downhill.
And Giant also interacted a lot with the Burbaches of famed B squared half H fame. I think he probably even wrote papers with Willie Fowler, my thesis advisor. And one of the things which I think is very worthwhile to remember is that essentially that steady state model in its incarnation is pretty much what is called eternal inflation now. It's just that the size of the bangs, which were called little bangs, are a little bit bigger now than they were then, and then the other ingredients which have been passed in, which I don't think were there, but maybe they were, which was quantum fusion and quantum tunneling are the key aspects of this picture. So the other aspect then is that in that framework, I think although there have been Jordan-Brahms-Dickey theories of conformal transformations and the importance of that to lengths, I would say that a really impressive pioneering class of work was Giant's work with Sir Fred, introducing conformal transformations and what you might get out of it, and in particular speaking of what might have occurred before the Big Bang, and that the Big Bang itself might have been a bit of an illusion. And we just heard Neil Turok and Paul Steinhardt say, roughly speaking, the same things, and the actual issues are not very much different than they were with Giant. So today I asked Giant to say a few words about, I don't know if you are going to, about the state of Indian astrophysics from his exalted perspective, and he's also going to talk about a search for very old stars, perhaps older than the W map age of the universe. We'll see.
Thank you, Dick, for your warm welcome here. This is my third visit to CITA and fifth to Canada. The other two were before CITA came into existence. So I want to say a few words about astronomy in India as it is today, and then come to talk. So basically I would say that in the last 20 years, astronomy in India has witnessed a revival from the very early days when early days I am referring to 1920s, when Meghnad Saha worked on the ionization equation, Saha ionization equation, and S.N. Bose worked on the Bose statistics. So what I like to say very briefly is today where astronomy is being done in India, what are the institutional support it is getting. So if you ask for some visitor to come and visit a place in India where he is interested in astronomy, I would mention two cities as the major places. One is Bangalore and the other is Pune. In Bangalore you have the Indian Institute of Astrophysics, which was set up by Venu Babu, who was an observational astronomer, and which controls the 2.3 meter telescope of Kavadu. Then you have in Bangalore Raman Research Institute, which has a major part of it devoted to astronomy and theoretical astrophysics. At one time, C.V. Raman, the Nobel laureate in physics, was the director and founder creator of that institution. And later his son, Radhakrishnan or Rag, as is popularly known among astronomers, he was the director. And they do work in microwave, radio astronomy and so on. In Bangalore also, the Indian Institute of Science has a group of theoretical astrophysicists working as a unit, and they are also contributing a lot to overall astrophysics in India. In Pune, you have two major institutions. One is the, which you may have heard of from radio astronomers, the GMRT, the Giant Interwave Radio Telescope, which is controlled by the CITA Institute of Fundamental Research. And the TIFR, as it's called, is based in, its main center is in Bombay, or Mumbai, as it's called now. And its offshoot in Pune is the radio astronomy group, which is NCRA, National Center for Radio Physics. And neighboring with that institution was our institution, the Ayuka Inter-University Center for Astronomy and Astrophysics, which was set up in Pune basically because the GMRT was going to be at Pune, and the University Grants Commission, which is the primary funding agency in India for universities, wanted a facility in the university sector to be such that it can have major usage of some national facility. And since the GMRT was coming up, they felt that if we are neighbor to them, we will be able to take advantage of it, and that has turned out to be right. So, apart from these, since I mentioned the Tata Institute of Fundamental Research, it is the major research institute in Mumbai, set up by Homi Bhabha in 1946, and it turned out to be the model institution for others to copy. And that is how we now have, apart from the Tata Institute, which covers a whole range of subjects in theoretical physics and mathematics, it also covers biology and astronomy and physics. So you have, therefore, a major unit which is supported by the Department of Atomic Energy. So in India you have different science departments supporting these sort of institutions. The first institutions I mentioned, the Bangalore institutions, they are mainly supported by Department of Science and Technology. In and Tata Institute is supported by Department of Atomic Energy. And they have also created institutions all around India. So there is one in Chennai or Madras, the Institute of Mathematical Sciences, which also does have relativities, physicists. Then you have the Institute of Physics in Bhubaneswar in eastern India. And apart from that, in Allahabad, in northern India, they have the Harishtandra Research Institute, which covers theoretical physics and mathematics and also astronomy. But in addition to that, A&A are done in a number of university departments, and the Ayuka was set up mainly to encourage that activity. And we have something like 100 associates who are university faculty members interested in astronomy and astrophysics. So if you think of some isolated university and some physicists in that university interested in astronomy and astrophysics, in his local environment he may not get any major support for his research. But if he is in contact with Ayuka, he can come and use our facilities and get even electronically action at a distance wise support from Ayuka. And these associates are entitled to visit Ayuka for any number of visits. They can come to 4 or 5 visits in the year, spend up to a few weeks. It all depends on their convenience, and their travel and living expenses are borne by Ayuka. So this model was basically a copy of Abdul Salam's Trieste Center, where the users are developing nations. So here the users are universities, and they are encouraged to use the center. In the last few years, we have turned greater attention to observational astronomy, which earlier was more concentrated on theoretical. So theory continues to get important support, but we also have additional interest in observational topics. So we have a 2-meter telescope near Narlikar, which was initiated, I think, in the early days by the Science Advisory Committee of the people who was a member. They proposed that this telescope would be desirable. So that has now been working. And we are also participants of SALT, that Southern African Large Telescope in South Africa. And hopefully we will join one of the major 3 large telescopes. I think it is now more or less decided by our internal community of astronomers to join the Caltech PLP group. But we are of course waiting for the green signal from the government, which is promised to us in the sense that they are sympathetic, but they will say yes at a later time. But hopefully not very well. So this is a basic scenario, and we hope that more students will come up, more postdocs will come to astronomy in India. There are positions also available, because if these major facilities, observation facilities are take off, we will more manpower, more human resources. But for that reason, career-wise, it is a good thing at the moment for young people joining A&A as part of research career. So this is basically I wanted to say about this paper, and in case you have any question, you can ask me now or at the end of this seminar. So now, if I may come to my main topic, it is a work done by 4 people who are listed there. Vijay Mohan, who is an observational astronomer in Narlikar, Ferdinando Patak, who is an observational astronomer from ISO in Kashmir, and Ken Freeman from Australia, and myself. So you might wonder how these 4 people got together. Of course, Vijay Mohan and I are colleagues, so that's not a problem. I had given a course of lectures in ISO in Kashmir, and Nando, or as we call it, Ferdinando, was one of the people in the audience, and he said that since we are talking about alternative cosmology, alternative to Big Bang, can you think of a test, observational test, which will support your idea, or put it more scientifically, which will serve to disprove your idea or disprove Big Bang? Because scientific theories can only be disproved and not proved in any sense. And so I suggested that we look for very old stars, and the reason is soon. And the question was, how do we look for them? And at that point, Ken Freeman happened to be visiting, and we had a discussion, and he was very much interested, and he suggested color magnitude diagram as a way of doing things. So we will consider that way here. So let us continue. So the cosmological motivation for this is that if you look at the standard Big Bang cosmology, it is usually defined in terms of a few well-defined parameters: the Hubble constant, then baryonic density, then non-baryonic density, and the dark energy. And the total of these 3 omegas, which you see here, is equal to 1.
Well, there's just that not don't point the arrow
So the standard cosmology is defined in terms of these, and if you take this model, then you can calculate the age of the universe from the Big Bang to the present time, and it comes out to be something like 13.72 years. Thus, there is a clear prediction that no object in the universe can be older than this figure. I would find it very hard if somebody produced an older object that it could be accommodated within this particular set of parameters. So, in order to test this cosmology, and of course the alternative also I will describe shortly, one must look for very old stars, because stars provide you with a kind of system which is well understood in terms of evolution, and one can therefore say what is meant by very old stars. Then one can also look at galaxies of high redshift. At higher redshift in the Big Bang theory, they should be old, they should be young. But if you find embarrassingly old galaxies at higher redshift, then there is a problem for the Big Bang. And one can also look at the dynamics of clusters and try to estimate how old they are. And in case we get into an age problem, that's fine. So finding an old system disproves the standard cosmology, but it could be consistent with an alternative cosmology if such a cosmology exists. So what we do next, before I come to the actual test which is concentrated on the first alternative, is to describe what I may mean by an alternative cosmology. So this cosmology was based or inspired by Ambachumian, the Armenian astrophysicist, who argued that there are many creation events where masses of objects or matter are ejected. So this statement here is one of the important problems confronting us in the study of outflow of matter and ejection from the nuclei of galaxies is the quantitative evolution of ejected matter. This refers equally to those galaxies of which the center parts show initial life, and to radio galaxies and to other examples with discrete ejection. And then he went on to say that the few facts at our disposal show that these data can make conflict with the law of conservation of energy and matter in its present form, and may perhaps require a generalization of this law. So in a sense, he was willing to sacrifice one of the holy cows of physics, namely the law of conservation of matter and energy. So in 1993, three of us, that is Fred Hoyle, Jeffrey Burgess and myself, proposed an alternative cosmology which was a variation of old steady-state cosmology, but which we felt was better able to cope with the observational constraints than the old steady-state theory. And it was called a quasi-steady-state cosmology. The reference is given here of the very first paper. And several publications since of the QSSCF since appeared in various research journals and conference proceedings. And if you want to see the basic ideas and the early work together in as a coherent piece of matter, you can see this book, Different Approach to Cosmology, published by Cambridge University Press, by the three of us. So this is the introduction of a alternative cosmology. So what is the QSSC? What are its parameters and epicycles? Because every cosmological theory starts with certain number of assumptions. So, similarly, with the Big Bang, there may be some assumptions which the alternative cosmology makes. How does it explain the present phenomena of relevance to cosmology? What new predictions does it make that distinguish it from the standard Big Bang cosmology? So, basic features of the quasi-steady-state cosmology are now being given here. So there is the underlying field theory which gives the equations of the theory. It's a theory of gravity that originates in Mach's principle and leads to gravitational equations similar to general relativity with the addition of a scalar field. So if you start with Mach's ideas of inertia being a function of distant matter in the universe, we can then set up equations which will define this relationship, and that leads us to this kind of theory. This is what Fred Hoyle and I had done in the 1960s. And the equations, if you write them in the standard form, the left hand side is the Einstein term plus lambda Vk. On the right hand side is the matter, but also a scalar field which has got negative elements. That is why this negative sign in front is a coupling constant. So from this you can derive the dynamical equation, and the cosmological constant originates in this theory from the large scale Machian interaction, and it has the right order of magnitude of the order of 10 to the minus 66 centimeters to the minus 2, but its sign is negative. That is, it has got attraction at large. So immediately when you see this, you will say that this will kill the theory because supernova observations require an accelerated universe. So the answer to that is that supernova observation can also be understood or explained by this whole framework. Instead of the lambda, it is the repulsive part of this negative energy CP which produces the accelerating part, and therefore you do end up explaining the supernova term. But here I am not going into those details. So when the C field arise from inertial contributions at the ends of all lines of particles and describe the dynamics of creation. Now we were interested in putting Batsumian's ideas into a mathematical framework, and the idea he was proposing was creation of matter at different distance and in small groups. So here we needed world lines of particles which have endpoints, that is where they start. And for example, one arrives and when one looks at all these mathematical equations, one finds that this happens provided the created particle has Planck mass, which is made up of the only constants appearing in the theory, C, H and V. One can therefore say that the creation of matter, the action principles from which the above field equations are derived, require the condition for creation to be the following, that Np square, that is the square of the mass of the Planck particle, is equal to the gradient of C whole square. Now this is a kind of conservation equation which tells you that if you are creating a certain mass, you are also side by side creating a negative energy equivalent to that mass. So this is ensuring your bookkeeping. So you are not sacrificing the law of conservation of matter and energy. Instead you are introducing negative energy as a viable key. And some people in the 60s objected to negative energy as unphysical. And but today phantom fields are in fact using exactly the same framework. So things have become regularized over the years. So particles can be created only where this condition is satisfied. That is the requirement. And one can therefore argue like this, that if you take CL and plot it against distance from a collapsed massive object like a black hole, but not exactly black hole but a highly dense object, then if you go by the Schwarzschild type solution, the CL is proportional to 1 over 1 minus 2 gm over r. And if r goes close to 2 gm, the CL shoots up. So it is possible near a massive object for this threshold to be crossed where it is equal to a square. If you go very far away, this won't happen. So if you have collapsed massive objects, they will induce creation of matter, and that is exactly what Ambassador was arguing. And if you create matter, then you also create C field. And C field being of negative energy, it will have repulsive effect and it will eject that matter outwards. So you get a creation event which will produce a mini bang type situation. So we call this phenomenon mini bang or mini creation event. So this is what where I use the word MC or mini creation event. Now what we proposed after this was that the universe is driven by such mini bangs rather than a singular one only system. So this mini bang can be fully understood in terms of energy conservation, and how the explosion arises can be understood also. So one could argue that instead of the original big bang, you have these mini creation events happening and repelling each other, because whenever there is local explosion, that repels matter away from it. So applications to cosmology came by making up cosmological models, and what we found, if I may go over. I will go over the basic process, but this overall scale factor of the universe, S of t, is made up of two aspects. One is an exponential expansion, which was de Sitter type solution in the old steady state case, but modified by this oscillatory term, which has got an up and down type of situation. Now, why does this happen? This is because, if we go back now to the earlier Hitchcock, if you have an expansion phase, imagine that the universe is expanding, that expansion will lead to a dilution of the background CP. And if the background CP gets diluted, the creation events become less and less effective, because they have to raise the CP from much lower value, and they cannot create matter, and therefore the expansion slows down because the creation process slows down, and at that stage the negative lambda makes its present strength, and if the distance is large, the force of attraction is large, and the universe contracts. And in the contracting phase, when it becomes smaller and smaller, the density of CP rises, and then creation centers become more effective, and the contraction slows down because of repulsion of CP and the bounce effect. So you have the universe bouncing from finite value. So you therefore see an oscillatory model with a long-term expansion coming from overall creation. So we can see here the nature of expansion. The S of t has got these ups and downs and an overall expansion. So typically we can say Q is a 50 gigayears and T is 1,000 gigayears. This is the universe. When I mentioned what are the fundamental assumptions, so one would say that the universe has two time scales. One is the exponential time scale of T, 1,000 gigayears, and short-term oscillatory time scale of 50 gigayears. And that parameter eta always turns out to be less than 1, so this lowest size of the scale factor never reaches 0. So the universe is always singularity free. And the present, one can fix the present epoch somewhere here by measurement of Hubble constant, because Hubble constant is changing. So if you look at the universe from now, today's vantage point, look back, you will see it was expanding in the past, but if you look very far back, it was contracting. So you have this situation that the universe has expansion and contraction phases, and one could say that each minimum value here, which has got maximum density of CP, will produce creation events or more creation events. So therefore, you have new matter being created and it forms into stars evolve and finish off, and so this goes on. And the radiation which was left behind by the stars which were finished in this way, the relic radiation, if you thermalize it, it will generate the present microwave pattern. That is the way it produces the microwave background. And so therefore one could ask, if you have old stars coming from previous generation, can you see them now? So let me just go back to the period since the last minimum is 14 gigayears. Here, if you count the time taken from the last minimum to here, it is about 14 gigayears. But if you imagine stars which were present here, which were found in this cycle, these stars, some of them will survive through the minimum phase because it's not all that dense phase, and it will come to the present. So if you look far enough back, you should see sources where stars were being born, and today their ages will be more than 14 years. So this was the motivation for looking for old stars.
But the control parameter is determining what the density is of minimum contraction is what the control parameter. So
Yeah.
you're going down and you're saying that it doesn't go to that big a density,
Yeah.
whereas the new age of big crunchers would say it's going to almost plankton density.
Here you can see the density at the minimum scale factor is not very large. It's about 200 to 500 times the present density. And stars in the previous cycles will survive if they are old enough.
But what controls that in the theory? It would be 200 to 500, which of course is remarkable given
Yeah.
given the what many of us think is true, which is that C and D decouples at 10 to the 9.
So, if you see here, the time, the eta factor is 0.8, which comes in the 1 plus cos this eta here. Now, if this eta were very close to 1, then the size of S will be very small, and 1 over S will be very large. Yes.
So I guess the related question is, that even though you're saying that CMB comes from the latest compression, if I understood correctly, have you quantitatively been able to predict the fluctuations in CMB? I mean, if so, how do you do that without having the kinds of compressions?
Sorry, what do you want to see?
He wants to get the acoustic peaks of the microwave background in this law.
Microwave pattern.
How would you explain the
Yeah,
remarkable
okay.
structure?
With such smaller, less severe
You see, the whole mechanism for production and thermalization of microwave background in this cosmology is different from the Big Bang. So, if you ask for the boomerang peak in the power spectrum, how does it arise? And the answer to this is that the stars of previous generation, they produce radiation which was thermalized. And how it was thermalized, I can say differently later, but let's assume it's thermalized. Then you will have a very smooth microwave background, except what is produced from the very last minimum, because it has not had time to get homogenized in the process. And so what you find is that you will see some signature of clusters of galaxies, where stars are existing whose light you have thermalized. So you should see this what we call inhomogeneity on the scale of clusters of galaxies, subtending a certain angle at you, depending on what is the maximum redshift. And this maximum redshift is no more than about 10 ohm. So this maximum redshift will suspend a certain angle, and that will show up in your power spectrum. And that exactly the panel matches the boomerang. And what I can say is that we had this result in print before the boomerang result was came into. So it was a genuine prediction and not a post. So similarly, one could argue that other peaks of plan on our map chart, would come from smaller levels of discontinuity, that is instead of clusters, there are groups of galaxies. And one could relate those to the peaks in power scale. So we had a paper on imagery of this. You can look at the scales. And I think Amir had done some work for us. Later. So here we come to this equation that can we identify stars which are old, which have come from the previous cycle within this was formed in the contraction. So how do we identify such stars? This was the problem which we started with. And one can argue like this: the stars of mass 0.7 solar mass will just evolve off the main sequence when they are around 20 gigayears. Similarly, a star of 0.8 solar mass will be 15 gigayear old at that stage. So when you start becoming giant stage, depending on how much mass there is, that will decide how fast they evolve and therefore how long they take on the main sequence. So what we decided was to look for, and that was Ken Freeman's idea, that we look for subgiant branches greater than the shoot corresponding to 15 gigayear old stars. That means if you take a standard HR diagram, you will find, I will come to that later, giant branches shooting off from the main sequence, and center you go, the stars which you are talking about are of lower mass. So we wanted to look for such stars. And where should we look for it? So one possible location to look for such stars was to look in the LMC, Large Magellan Cloud. So why do we look for LMC? Because in the quasi-steady state cosmology, such stars will have been born in the previous cycle, and since the mini creation event activity grows close to the minimum of this, there will be many explosions in the galaxy to eject these stars into the outer boundaries of the halo. So, if we look in the halo, we should find such stars. That was our suggestion, and the best place to look for was in the LMC. Which is the south of the galaxy. So what is the advantage of LMC? Why we choose LMC? Because it is on the doorstep of the galaxy, it's not very far. One can resolve individual stars in the galaxy. Then the distance to LMC is well established, so there is no distance problem. And reckoning in line of sight is small. So the dispersion in D1 is really small. And the foreground contamination is low because they are on the high latitude. So we are not facing many stars from our galaxy. So these were the reasons why Ken Freeman suggested we look in the LMC. So to look for very old stars in the LMC, we need a deep survey in D and I of a large field in the outer disk of the LMC, away from the regions of local radiation. So it shows these criteria. And here you see the HR diagram. You have main sequence like this, and these are branches. And depending on where you are branching off, the age is decided. So the further down you go, the age increases. So this was the reason why we said that to look for very old stars in the LMC, we need a survey in V and I of a large field in the outer disk of LMC. If such a distribution is available, one can place isochrones on the color magnitude diagram and look for very old subgiants. So that was the idea. And the expectation was that there should be a few tens of magnitude fainter than the subgiant branch of the conventional old stars with the LMC the values, if you look at the D magnitude and D minus I, we expect somewhere in this region if you are to go further down for very old stars. So galactic contamination can be estimated by using the Besançon model of the galaxy, which tells you how the stars are distributed in our own galaxy. And the galactic foreground stars can be excluded by measurement of radial velocity. That I will come to later. So the observational data which we used was of two kinds. One was the archival data from Hubble Space Telescope, and the second was we put in an application for observations of certain zones with ISO and 8 meters. We were given some 20 hours observations and we managed to get some data there. So I will come to that later. So this table 1, which you see here, indicates 7 such fields which are shown here, HST fields, for which the HST observations exist. And the figure shows the CMD color magnitude diagram for all stars in these 7 fields. So all these are the stars. And one can see the main sequence and the giant branch. You can see something coming out here. But there seems to be a mixture of populations of different ages and metabolism. So you have a variation. For example, here the color magnitude diagrams are put in. The blue one is 15 gigayears and the red one is a binary version of 15 gigayears. That means you make the assumption that the star you are seeing is not single one, 2 stars superposed. But I will come to that again. So for our analysis, only those stars have been chosen for which the error in V minus R is less than 0.02 magnitude. And on the HST color magnitude diagram, we have overplotted darkness isochrones reddened by this. So we put in the expected reddening together with a shift due to distance modulus of this corresponding to Z equal to this and ages. So we have plotted color magnitude diagram for these ages population. And the data can be fitted by a combination of these isochrones, which at first sight indicates a population older than 20 gigayears as well. I will come to right now. Here you see these isochrones and the data which we finally, from the very dense data for these data, these are the isochrones corresponding to different ages. So this red one is 25 gigayear old and the green one is 20 gigayear, blue is 15 and 10 gigayear for this purple. So then there is a binary isochrone which is drawn here for 15 gigayear. Now, so you see that the number of stars that you are trying to understand in the giant branch seem to be a mixed population. So one could ask, are the unresolved stars their optical doubles and binaries? So what we did was we plotted a binary star sequence shifted by 0.75 magnitude to allow for the fact that you are seeing 2 stars in place of 1. And further reduced by 0.06 magnitude to take account of 3 sigma error in V minus R. So we wanted to push the theory as far as possible, corresponding to a stellar age of 15 gigayears. So the stars bluewards of this sequence would be younger than 15 gigayears. That is what happened. And on the other side, redward of this sequence will be older. So there are stars which lie below 15 gigayears, I said so, the blue one, and to the right of the binary isochrone, which is black. So if you take to the right of this and below this, you see a certain population of red stars. And these stars don't seem to fit into anything younger than 15 gigayears, and even if you assume the binary, you still require a 15 gigayear age.
Can you just give an indication of what happens if I vary the extinction of an ethnicity to one of those isotopes? How does it shift around with
Yeah, if you
E and with an ethnicity?
you can shift them around if you change the metallicity or
Or the
introduce what you call photometric errors if you are if they are long bigger.
And what does that do?
Yeah, I will come to that.
Okay.
So if you have first of all photometric error, these stars in red have larger photometric error. So if you look at the population and you simulate the plot, you find that these are on this both sides, they are more than 3 sigma error, and these are what you would expect to be present in normal variation of errors in photometry. So if you do this, you can ask, do the stars in red, which were on the outside of that black patch, they have larger photometric error. So if you plot dBi, which is recovered V minus I minus simulated V minus I, against the V magnitude for this star in the range of interest, which was this V magnitude value, satisfying zero crowding and error in V minus I less than 0.02. Then only 1% of stars statistically are greater than 0.06, whereas in the real sample, the red points are 42 out of a total of 1549. So much more than the 1% you would expect, 3 times that 1%. So far too many to ascribe to errors. So we cannot say that all the red stars are coming from photometric errors. Then we could also ask to estimate the number of field stars of the galaxy, use the Lagrangian model. The model simulations cover an area of 4.1 square degrees, 9 times the area covered by HST delta, and lead to a CMP shown in this figure. So these are simulated stars, assuming they are foreground stars in our galaxy. So we can ask this question. We have superimposed the same set of isotones on this to give an idea of the number of foreground stars present in the data. The number of stars present, red words of the binary sequence, red words of the black, red word is on this side, have been plotted in red color. So these are the red stars, red color stars, which come from Lagrangian model. That is what you would expect from foreground stars. So, how many excess stars are you seeing? So each HST field covers an area of 5.72 square arc minute. So the total area of 7 fields is around 40 square arc minute. The number of field stars predicted by the simulation model for the equivalent area and in the region of the suspected old stars is only 2. And the number of stars in the HST data in the same region is 100. So we are seeing far too much than what you would see in a foreground population. Now if you use that photometric error criterion, that 102 can be reduced by a factor 3, let us say, so you can come to something like 30, 35 stars, which compared to 2 is still statistically very much higher. So we don't think that these excess stars are due to foreground population of the galaxy. So the other point is the excess number varies from field to field and is hence more likely to be intrinsic to each field rather than a foreground contamination. That is what is. Then what about background count? So if you look at very distant alien and USO count and ask whether they are spoiling the overall effect, the answer is the expected number in the HSTP will be of at most 3 of these in the given magnitude range. And thus the background contamination will be negligible. So the LMC option says that if these stars belong to the LMC, the isochrones that fit naturally belong to stars older than 15 gigayears. The turn-off point of the subgiant branch is higher than the turn-off point of the normal LMC star. And that is in the LMC CMT color matrix diagram. Such point will be fainter than 22.6 magnitude, so will be below. Any star redwards of the binary sequence and fainter than this limit is a potentially old star. This is our conclusion. So we can ask, can we bring in the criterion of radial velocity? The answer is yes, we can do that in principle. Radial velocity measurement will provide another check. The LMC radial velocity is around a mean value of 270 kilometers per second, whereas the galactic halo stars in the direction of LMC have a mean velocity of 190 kilometers per second with a dispersion of 90 kilometers per second. The spectral measurements are able to distinguish between galactic and LMC stars. So what we propose is for a future study is a spectroscopy which will give us some radial velocity. Then if stars show velocity is high enough to be near the LMC velocity, then one can use spectral measurement of gravity to distinguish between main sequence star of a subgiant star. If a significant number of stars show high radial velocity, then they must be identified with LMC, and the above interpretation of very old stars would apply to them. So this is the basic thing. Now what happened to the DLT's observations that we did? The VLT survey of another field covered an area of 0.05 square degree centered around this. This area lies around 9 degrees from the LMC center. The area was chosen to avoid crowding and also to be away from the region of active star formation. So when we did that, we found that there are not many stars which come in that region where we found the testing. And if we compare with the Brigantine model, here there are 7 stars and the simulated model gives 8. So therefore there is a satisfactory fit, and we don't need to say that we are looking at, we are not looking at line of sight stars. So this is an example of the case where stars which apparently look like old stars are actually not so, they are line of sight stars. So this example therefore did not help our finding of old stars, but it at least underscored the fact that there are 2 kinds of distribution which we are facing. Then we can look at alternative interpretation. Can we explain everything with higher metallicity? So the answer is we can fit the data with isochrones of 10 gigayears, having solar metallicity and making it a binary isochrone further reddened by 0.06 magnitude to account for 3 sigma error in V1 star. So we can shift the whole thing like this here and say that all these stars are therefore not old. But we have made certain sacrifices in making the metallicity as much as the solar metallicity, which is not the case for LMC. Another possibilities are these stars, not giant stars, but pre-main sequence stars, which are on their any tracks. So in the figure below, we have plotted the LMC data with pre-main sequence stars. The isotones are drawn of 7 million years in red and 20 million years in cyan, corresponding to Z equal to 0.01. So if you see that, you can get an explanation, but the problem is that if you look at the distribution here, you find a certain difference between in two areas and the others are giving small numbers. So since a star of solar mass spends about 30 million years on the eddy track, some of this could be found in regions of young stars. But this explanation will be hard to understand why one sees a large number of such stars in only 2 of the 4 young fields. So why is star formation occurring only in small fields and not all neighboring fields? So this becomes a somewhat contrived situation. So if we look at excess radiation, that is, if we take 15 gigayear isotone with Z equal to 0.04, E equal to this, and the binary sequence, you see that the binary sequence can explain the data region well. You can get this thing going through this data region well. But by modeling the LMC as having one can also make these stars go further away in LMC by saying that LMC is having a halo of 10 kiloparsec size. We can ask if our candidate old stars are not the faint old stars, faint stars belonging to the furthest section of the halo. We can raise this question. The green isochrone of the figure below shows this result. So this you can get something explaining these stars reasonably well. But one will need to increase the distance of the remote part of the halo in order to explain our population of faint stars as belonging to it. So if you want to push them further away in LMC, you have to make the halo of LMC bigger, which is also not required, and it is not very feasible. So one could say that there is a prima facie evidence for very faint stars belonging to the LMC being very old, around 20 gigayears. Other explanations, including binary stars or three main sequence stars, are also possible, but they in turn require somewhat contrived assumptions. And spectroscopy may resolve this uncertainty to some extent by looking at the possibility that they are line of sight stars or belonging to LMC. Although the present technology will be stretched to the limit in order to generate those data, because to do these spectrum at that faint star is not really easy. So I think I will stop here.
Questions?
So what determines the rate of matter creation in the black hole horizons in this model? And do you expect black hole terminology to be different than what we expect to do in fusion scenarios?
You mean the matter creation mechanism around the black hole?
Yeah, right.
Yeah, the scenario here is that you have in the universe objects which are not the strict black holes of relativity which have gone inside the horizon, but near black holes, that is, which have come close to the horizon. Because one can show that if the C field is present, the collapsing object bounces. It cannot go on switching to singularity. And it snaps, it bounces just outside the event horizon.
So the claim then is that what we think are black holes aren't,
Therefore,
what we think are black holes aren't.
so what we would say that you have very dense conglomeration of objects, but they are not technical black holes that relativity process. And what astrophysicists find as black holes in the centers of galaxies are in fact these conglomerations of density.
But they're stable objects that would be black holes. They don't oscillate.
Yeah, when it oscillates and it bounces, when it bouncing at the minimum radius, at that time it will be very thin. It will collapse because of the visual gravitation of the redshift and the collapsing. But when it bounces back, it can generate a blue shape on water. So you should be able to see it as basically white.
Could I ask a quick question? So, did I understand, I mean, it's a sign convention here, but F positive corresponds to negative kinetic energy. Right? Is that right? Yeah. So, the mantra would be, you have injected a ghost into the theory, and it would, people would say, hey, that's not very good thing to do. And usually people say the theory is sick because of a ghost. So is the theory fully self-consistent as one considers quantum behavior, with the field? I mean, the same issue, of course, arises, except that people include a potential with any sort of phantom energy, which, in fact, most people would say is a pretty sick theory in this day and age. Right? Because, among other things, I mean, I think if you were not crossing the phantom divide, because you were always maintaining yourself, is that positive? Is that correct? An earlier version of your model, you had I think you actually had almost a singular term, and you made that the function of water or something. Is that right? Is that what I misremembering? I just remember that there was a situation which was much more, not outrageous, more high energy than this one. And I am rather surprised to hear that the bang is actually, the bounce is actually occurring at such a relatively low density than the current version of the wall.
Yeah, I think where the bounce will occur overall depends on the mass.
Yeah, but it also depends upon exactly what that F coupling factor would be.
Yes. You mean that constant F.
Well, but it doesn't have to be a constant.
So, what one can do is apply this model to a specific problem of collapsing of seawater. So when you do this, you find that the parameter that on which you can base your answer. What is the initial mass of the object? And what was the initial sea fish? Because then the going to dynamic will become. So you can vary one or the other or both. You get a whole range of bounds that has been done. What we have not yet managed is quantize this, because that is a hard one, because it reacts back on the back reaction problem.
Any questions?
You have just the two colors, BMI, for your photo magnitude diagram.
Speak up.
So, you have two colors.
Two colors.
So if you got more colors, would you be able to distinguish between multiple stars and
You mean in the CMD?
yes, rather than having to get full spectrum?
So what we have done is taken different models, that means models of different masses, evolved them. We take the color magnitude diagram and each color corresponds to certain range.
Right.
So for these are just our distinguishing between different range isotopes.
But if you have say a binary star and your colors are from a binary star, that would look very different if you got a third color. If it's a binary versus
Yeah,
this.
what people do, this is not really my teach, but I don't know the detail. Then they take a binary star, and if they are very close to each other, the two binary, then you will see them as one single star. And you will then ascribe a greater luminosity to that of that star than each one of it. So So they make a correction for that, so this block is happening. So that magnitude change of 0.75 comes from this.
Okay, on that note, we'll go up and have coffee and cookies.